All right, this is section 13.3, shifting equilibria. All right, so let's just start with, let's just cut to the chase. Le Chatelier's principle says an equilibrium will move so as to counteract an imposed change. So let's use this classic equilibrium as an example here. So we've got N2O4 reacts to give 2NO2. So let's just ask ourselves the question, what would happen in that system if it's at equilibrium and you add more N2O4? Well, if you add more N2O4, you've imposed a change on the equilibrium, and that is you've added more N2O4, you've increased its concentration. So according to Le Chatelier's principle, the equilibrium will move to try and counteract that imposed change. The imposed change is an increase, so it will try and move to counteract that increase. How would it decrease the amount of N2O4 then? Well, obviously the equilibrium would move towards the right, and that's indeed what happens. So that's one example of using Le Chatelier's principle. Another one would be the one I've given here, increasing pressure. So now before we do this, just so you realise, the more molecules you have, the more pressure that gas will have, obviously. So if you increase the pressure on this particular system here, the equilibrium will move to try to decrease the pressure. The way it can do that is by trying to decrease the number of molecules. How would it do that? Well, if you notice here, you've only got one molecule of N2O4 reacting to give two molecules of NO2. So to decrease the amount of pressure, you want to decrease the amount of molecules, the reaction would actually move to the left. In other words, you've now got less molecules. So that's indeed it. Now, I've given you another example here where I've got a reaction of N to O2. Oh, this silly crazy thing's working now, of course. Let me just put the pen on here. We've got N2 and O2 reacting, and you end up with 2NO. Now, if you look here at this equilibrium, on the left-hand side of the reaction, you've got two molecules in total, producing two molecules on the right-hand side in total. In other words, if you change the pressure here, there's no way the equilibrium can move to try and increase or decrease the pressure because you've got equal numbers of molecules on both sides of the equation. So for a temperature, how can you use Le Chatelier's principle? So in the example I've got here, you've got N2O4 reacting to give 2NO2. Now, I've got a delta H value there. Now, delta H means change in heat, which is actually change. The technical term is enthalpy. And because it's written as a plus term there, I know this might sound a little bit confusing. In front of that 57 kilojoules per mole, you can imagine there's a plus there. It means that it's actually absorbing heat from the system as it's read from left to right. Now, I can write that in the equation. So it's now on the left-hand side of the equation. And now we've got an equation we can work with in terms of Le Chatelier's principle. So what does that mean? Well, okay, let's say we increase the temperature. Well, if you increase the temperature, that's the imposed change. The counteract to that will obviously be to try to decrease the temperature somehow. And if you think about it for a moment, as the reaction's written here, reading from left to right, it's actually sucking heat into the system. In other words, it can decrease the temperature. And that's indeed what happens. And so therefore, when you increase the temperature for this reaction, the equilibrium will move to try and decrease the temperature. In other words, it will move towards the right. Okay, just a heads up on a couple of things when you're working through the questions, etc. First one's this one. If you're looking at solids, the concentration of a solid, in case you've missed it, is a constant. It doesn't change. It is what it is. It's the amount of stuff in a volume, and it doesn't matter how much you've got. the concentration of it's always the same. And so when you're trying to calculate equilibrium expressions, which are based on concentration, the thing is you don't put in the concentrations of solids because they simply don't exist. So here's an example here where we have solid AB, which ends up solubilizing, I think you can see here, in water to produce A plus aqueous and B minus aqueous. So this could be, AB could be sodium chloride, for example, and you end up with sodium ions and chloride ions. Okay. Now there's a thing called the solubility product constant, which is basically an equilibrium constant for how soluble ionic solids are in water. And when you write out the equilibrium constant, you'd initially start by writing, okay, it's products over reactants, so it'd be A plus multiplied by B minus divided by what? Well, it's the concentration of a solid, which is a constant, so you don't write it in. There's no need to, so that actually gets left out of the equation. So that's the first thing that you should be aware of, that solids are a little bit tricky in this system. The other thing is that often when we're looking at equilibria, we're actually looking at dilute solutions, and that includes, and mostly, of course, things are in water, particularly if we're talking about acids and bases. And I don't know if you kind of realise it, but the concentration of water in water is going to be a constant, and so therefore it's often not included in equilibrium expressions either. So if I have an equation like this, where I've got H2O splitting up to form H plus aqueous and OH minus aqueous, and I write down the equilibrium constant for water, so rather than using KEQ, I'm going to use KW. It's going to be products over reactants, so it'll be H plus concentration multiplied by OH minus concentration divided by the concentration of water, but that's effectively a constant, so that gets left out of the equation. Now I'm just giving you a heads up about this because we're going to use this next week, but just be aware of that. And the equilibrium constant, by the way, for that reaction at room temperature, which we take to be 25 degrees Celsius, is 10 to the minus 14. Okay, so that's the end of chapter 13. You should be good to go.